Welcome to this explainer. Today, we're diving straight into the invisible world of atoms. We're going to look at exactly how ionic bonds form simply through a pretty neat little game of give and take. You know, it sounds super complex, but at its core, it's really just about finding balance.
So, let's start with a really fascinating question. What actually happens when atoms start trading tiny parts of themselves? Like, how does this microscopic trading floor create the very real, everyday items we rely on? You know, like the salt you literally just sprinkled on your dinner. Well, we're going to break down that exact process today, step by step.
Section 1. Atoms to ions, finding balance. Okay, so atoms in their natural state can sometimes be, well, a little bit unstable. And to fix this and find that perfect balance, they make a really simple trade. They either lose or gain electrons. And the moment an atom makes this trade, it transforms into what we call an ion. Now, what's super interesting here is the fundamental rule of opposites. Because electrons carry a negative charge, the math can actually feel kind of counterintuitive at first, right? If an atom loses one of these negatively charged electrons, it sheds negativity and gets a positive charge. Bam, it's a cation. I mean, losing negativity makes you positive. Honestly, that's just solid life advice right there. On the flip side, gaining an electron brings extra negativity, creating a negative anion. So, lose a negative, become positive. Gain a negative, become negative. Makes sense, right?
Section 2. Opposites attract, ionic bonds.
Let's look at sodium chloride, which, you probably just call standard table salt, as a perfect example of this process in action. Step 1. We have a sodium atom. It's a bit unstable, so it happily gives up one of its electrons. Step 2. Along comes a chlorine atom, which is desperately looking for an extra electron to become stable, and it eagerly snatches it up. Now the sodium is a positive cation and the chlorine is a negative anion, which brings us to step 3. Just like invisible magnets, those opposite charges immediately and powerfully pull them together.
So here's the absolute crucial point. This bond isn't like a physical string or molecular superglue holding them together. Nope. This powerful, invisible magnetic traction between the positive cation and the negative anion is exactly what we call an ionic bond. That's the whole shebang. It's a relationship built entirely on the simple give and take of electrons to create this perfect, attractive balance.
Section 3. Building common compounds.
Check this out. This illustrates exactly how these pairs balance out in the real world. Beyond our classic table salt, sodium chloride, we get totally recognizable names here, like magnesium oxide, potassium chloride, and magnesium chloride. In every single one of these examples, a positive and negative ion have basically traded electrons and locked together through that magnetic-like attraction. They've created something entirely new and totally stable.
But you know, sometimes a simple one-to-one trade just isn't enough. And this is where it gets really fun. Magnesium, for example, naturally wants to lose 2 electrons to become stable, which gives it a positive 2 charge. But wait, a single chlorine atom only wants to gain 1. So what happens? Well, the magnesium atom simply pairs up perfectly with 2 separate chlorine atoms. It hands 1 electron to the first and 1 electron to the second. Boom. Everyone is happy, the charges balance out to an absolute 0, and they form magnesium chloride. It's literally like a giant puzzle perfectly clicking together.
Section 4. Ionic compounds around us.
So why does all this matter? Well, the reality is these ionic compounds are absolutely everywhere. They literally drive the functions of our daily lives. Think about the health sector. These compounds are the essential body minerals listed right on the back of your daily supplements. In agriculture, they're the key ingredients in fertilizers that, grow our food. Industry relies on them heavily for manufacturing, food prep, and creating super effective cleaning supplies. And right in your own home, understanding these basic formulas helps you read labels so you know exactly what you're bringing into your house.
You can actually find these safe household examples hidden right in plain sight on a salt package, a fertilizer label, a food label, or, a supplement label. It is incredibly important to be able to recognize these chemical names, because when we actually understand what potassium chloride or magnesium oxide is, we can handle these materials responsibly, safely, and honestly with a real appreciation for the microscopic science that's making them work behind the scenes.
All right, we have covered a lot in this explainer today. So here's my challenge to you. Take a look around your house later. Pick up a supplement bottle, or maybe a bag of potting soil. And just think about the fact that the physical reality of those items is held together by billions of invisible, microscopic magnets, playing this continuous, elegant game of give and take. So tell me, next time you check a food or fertilizer label, which invisible ionic bond will you spot hidden in plain sight first?